Hello everyone. Today we will be listening to the third colloquium talk for DRP Turkey from Pelin Güven Geredeli. She received her PhD from Hacettepe University and held postdoctoral positions at the University of Virginia, Politecnico di Milano, and the University of Nebraska-Lincoln. She is currently a faculty member in the School of Mathematical and Statistical Sciences at Clemson University. Her research focuses on the mathematical analysis and numerical computation of fluid structure interaction systems, particularly in biomedicine and aeroelasticity. Today, she will present her talk entitled Interactive PDE Dynamics Arising in Biohealth and Aeroelasticity. Well, Pelin, it's your turn.
So I guess I should start with a big thank you for making me part of your colloquium series. So thank you so much for the invitation. As I see, DRP is an interesting and exciting program, and what I can suggest at this point is just please continue to organize such events in Turkey, which is probably one of the things which we need in our country to improve the science. So please continue to do this. So you already made a great introduction about me, but let me also just say something about my work before starting my slides. I got my PhD in Hacettepe University as an applied mathematician. So basically in my PhD, I worked on the qualitative properties of some partial differential equations. So there were a few models actually. I'm very sure most of you are familiar with ordinary differential equations, maybe also partial differential equations, let's say the parabolic models and hyperbolic models. But when we say qualitative properties, we mean we are looking for the wellposedness, which means that the existence uniqueness of the solution, and then the long-time behavior of the solution. So these two things, two subjects were the main focus of my PhD thesis. But then recently I started to work on some interactive dynamics, which means that I'm looking at the interaction of two or three different partial differential equation models. So there is an interaction between them. So this interaction gives rise to some different modeling and different dynamics, which has a lot of real-world applications. And today, my talk will focus on the applications which arise in biohealth and aeroelasticity. Okay, so let me start with the outline, what I will talk about. So since we talk about the partial differential equations, of course, we call them dynamical systems. So I will explain why we say dynamical system for these equations. So I will mention about these kind of what we mean, what kind of dynamical system we expect. And then in my work, if I have a dynamical system, in order to analyze those qualitative properties, for example, wellposedness, to prove there exists a solution or the solution is unique, I mostly use operator theory, so operator semigroups. So I will mention about what is the relation between a PDE and the operator semigroup and how I use these two things. Then, as I said, basically in my works, I look at the wellposedness and long-time behavior of the solution. So I will just talk about these two phenomena for the PDE models I work on. And then I will just immediately focus on the applications, how we see the mathematical modeling as a biological application, biological or engineering application, let's say. So one of them is going to be the multilayered composite structure interaction PDE model, and the other one will be compressible flow elastic structure interaction model. So what we mean by them, I will just give in time. As a starting point, again, not everybody has to work partial differential equations, or not everybody has an interest in applied math. So what do we understand by saying qualitative analysis or quantitative analysis for partial differential equations? Okay, so so I am doing PDE analysis, but what do we mean? PDE analysis means you can look at the things from the theoretical point of view, or you can look at the things from the numerical point of view. So if you look at the theoretical, which means that you are trying to prove there exists a solution, but we don't know what the solution is because PDEs are generally very complicated and it's not possible to solve them mostly if it's not a very, very canonical model. So we can only say there exists a solution, or if the solution exists, it's unique. So how can we say this? Of course, we have a recipe. So just like in everything, if you are cooking something in the kitchen, you follow a recipe, right? So we do the same thing in order to prove wellposedness, existence uniqueness. We use some theory from functional analysis, real analysis, or some other analysis stuff. So this is the theoretical part. The other thing is, of course, while we are using the functional analysis theorems, we go deeper and deeper, and we use operator theory, which means that I will now connect my work with the operator semigroups, and then much deeper, we do some spectral analysis for the PDE system. But of course, how we use these things, I will show them in the following slides. So this is the qualitative part. But some people might want to look at the things from the numerical point of view. So instead of proving the existence uniqueness of the solution or analyzing the long-time behaviors like the stability, they prefer to look at the solutions from the approximation point of view. So again, as I said, we can't explicitly show this is the solution to my PDE. We can't do that. So what we can do, by using some numerical analysis techniques, we can approximate the solutions by using some algorithms, or you can derive your own algorithm to give a best result, to give a best approximation to the solution. And then you can just use some simulation to see, yes, my solution to this complicated differential equation will seem like in this graphics, for example. So for this, if you are looking at the things from the numerical point of view, then you can use too many packages. Some people use finite element methods, finite difference methods, finite volume methods, or monolithic approach. There are too many things. Nowadays, people use Phoenix, or here, MATLAB, Python. So people use too many things to do that. So when we say PD analysis, we categorize it in two ways, theoretical and numerical. Okay, so let's start with since I'm working on the mostly on the theoretical part, although recently I'm interested in the numerical analysis too, but mostly I'm doing theoretical. So if you are looking at the things from the theoretical point of view, so what you need to do, of course, the first question is you have a very complicated partial differential equation system. Is there any solution for your system? Because if there is no solution, then it doesn't make sense to work on this kind of problem. So the first thing, how can I prove the existence of the solution or non-existence of the solution? So of course, it depends if your problem is linear, or if your equation is linear or non-linear. If you are working with a linear equation, then you are lucky because you can use many techniques to follow the strategy to reach out the existence of the solution. But if you are working on a non-linear equation, then of course techniques should be different. Then you need to use some certain multipliers to get some energy identities or inequalities. This is more difficult. But basically, let's start with saying a dynamical system. So because in each case, it's linear or nonlinear. For the partial differential equations, we call dynamical system. So what do we mean by a dynamical system? A dynamical system is described as a particle or the ensemble of the particles whose state changes over time and obeys the rule of a differential equation, which is given via the time derivatives. So if your differential equation has time derivatives, then we say evolution equation. I don't know if you have ever taken OD class. Generally in OD classes, we mentioned about the canonical forms of parabolic problems, and we say heat equation, or for the hyperbolic equation, we give an example to wave equation or elliptic equations. For example, elliptic equations don't have the time derivatives, so they are static equations, so they are not the evolution equations. But parabolic and hyperbolic equations, or wave or heat equation equations, are described as evolution equations because there are time derivatives inside. Okay, so for a dynamical system, we have a differential equation which has time derivatives inside. So if you have time derivatives, then automatically you have the evolution of something. But what is this something? Of course, it depends on your model. What are you modeling in your equation? So you might model the flow of a water in a pipe, or oscillate. We generally give example in OD classes, the oscillation of a pendulum, or if you remember again, in OD classes as an application of the separable or linear equations, generally we give population dynamics as an example, and all these equations refer to evolution equations. So in them, with respect to time, for example, your population changes, right? In 10 years, what is the population going to be in this village, for example? We generally ask these kind of questions. So after knowing that what is your something, then with respect to this something is going to refer to variables and the state space, and state we call the state variable. For example, if you look at this equation here, this is just the basic first order equation. X prime is equal to f of x. F is a function here, or f might be a matrix. So here the rule is determined with this formula, and the rule is determined by f, or by this matrix A. So if you have this kind of equation here, let's say f is a linear function. In this case, again, just remember from the population dynamics, we were giving the solution to this kind of equation via this formula by using this exponential matrix, right? So e to the power at, A is a matrix here, f, just say this is 2 by 2 or 3 by 3 in the simplest case. So the solution is given with respect to this equality where x0 is the initial condition. And actually this equation tells us a lot of things. Actually, by using this kind of relation, I will connect my work via the operator semigroups. Why I say that? Because again, from the very complicated PDE, I will just reduce my PDE into this kind of equation to solve. And then the question is, if I have a linear equation, can I write the solution in terms of the exponential matrix? If I can do that, I'm good to go, because everything, now I have the recipe to follow. Okay. Again, as I said, I haven't shown you any complicated PDE yet, but now you will understand what I mean after seeing the complicated PDE. So I will have a very, very long expression in terms of the equations. It looks horrible, very terrifying. How can I solve this? Again, by solving, I don't mean to find an explicit solution, because generally this is not the case. Again, for solving it, I mean if I can prove the existence of a solution. So my starting point is, I start with my complicated PDE, but I reduce it to an ODE system, which I'm more familiar with. So from the ODE classes, we already know how to deal with this kind of equation. This is the first order, okay, differential equation, and I have the initial data. So A assumes a linear operator, so which say this is modeling this equation, this part, PDE dynamics. So if you can reduce your complicated PDE into this kind of form, then you might start to ask if your problem is well posed, which means that is there any solution? If there is it unique? and if the solution depends on the initial data, continuously depend on the initial data. But everything actually is based on this operator A. So why I say that? So here, this is the connection with the operator semigroups. After reducing your complicated PD into an OD system, now the solution is, can I define my solution? Because I'm looking for the existence of a solution, but what is the solution? This U. I'm looking for U of t. So the question is, can I write this U of t in terms of an operator semigroup just like that? If I can do this, if I can describe my solution via an operator semigroup, then all the theory in functional analysis or real analysis is given on the operator semigroups. So I have a recipe to follow for the operator semigroups to explain what is my solution and how the solutions will behave in infinite time or for some big time. So this is the key point. Everything is just based on writing my or describing my solution via the operator semigroups. Again, in order to do that, my equation has to be linear because we don't know anything about nonlinear operator semigroup theory, although there are some works, but it's complicated. So the first requirement is I should have a linear differential equation system, and then I should be able to write my solution via these operator semigroups. So what do we mean by an operator semigroup, ST? Some of you, I'm sure, are working on algebra, and is there any connection with a group or semigroup that we understand from the algebraic point of view and this operator semigroup? Yes and no. Yes, there is a unique solution. There is a unique definition for semigroups, semigroups or groups. But here, when we say semigroup, what we mean, of course, we are talking about a dynamical system, and we just adjust the semigroup definition that we understand in algebra into a dynamical system case. So what we say, actually, we have a dynamical system, which means that we have an evolution equation, and we denote this dynamical system as a pair of objects where X denotes my state space, so where I'm working as a space, and ST represents this operator semigroup, or it's actually, when we say operator semigroup, it's going to model my differential equation. And so with respect to this dynamical system, operator semigroup is a kind of mapping going from the state space X to X, and this X is generally, we prefer Hilbert space. It can be Banach space or norm space too. As you see here, any complete metric space is okay, but generally already we are working with the Hilbert spaces. And when we say operator semigroup, it's kind of mapping which satisfy these two properties, which means that your operator ST, when t is equal to 0, which means that the initial point, at the initial state, at the initial time, it should give you identity operator. And when time evolves, ST, which means that at time t plus tau, it should actually seem as a composition of these two operators. Of course, you are applying here, for example, S0 ut means ut plus 0. So this is an identity operator, so S0 ut means ut. Or if you just apply this operator to, for example, U0, it means that U0 plus t plus tau. So at every time, your trajectory U or solution just comes to a different time. That's the reason we call it as an evolution. It's changing with respect to time, your state position. Okay, so now, since we know the definition of the operator semigroup, the question is, can I describe my solution via this operator semigroup? Okay, if the answer is yes, now your solution is given with this equation, where U0 is the initial condition. And then if you can do this, since the theory is given for the operator semigroups, you can look for the long-time behavior of the solutions, for example. And in applications, in real-world applications, if you have the solution to your PDE, we call, for example, long-time behavior or large-time behavior, how the solutions will behave in large time. For example, just basically think about an ODE in population dynamics. We say initially when in 2000, for example, in the year 2000, the population of this village is blah, blah. And in 100 years, what is the population going to be? So you have a you have an OD model, and with respect to your model, you can solve it, of course, by using the separable or linear equation theory, and you can just analyze the long-time behavior of the solution. So in some certain time after some t large enough, what is the population going to be? So this is kind of the stability or long-time behavior and analysis of the long-time behavior. We generally call this long-time behavior, but actually some people say control theory, or we say stability of the solutions, or non-stability, for example. Okay, so now let's go back to the equation. So we said, okay, there is a connection between PDE, reduce it to an ODE, and then in this ODE, you have a linear operator A. So we said there is an operator, if there is an operator semigroup, we can look for the solutions and we can analyze the long-time behavior, but we haven't mentioned about what is the connection between the operator semigroup and this A, because all of a sudden, from this equation, we just jumped into this kind of solution and A disappeared. Actually, it didn't disappear. This A is called the generator of this system, just like from the algebraic point of view. So if you have a group, you are looking for what is the generator of this group. So we have a semigroup of operators, and then this A is going to be the generator of this operator semigroups. And by looking at the properties of this A, we follow the recipe and we prove the wellposedness and we look at the long-time behavior. So A plays a key role here. The structure of A, of course, it's not unique. It depends on your model, your PD or OD model. So I will actually mention about it in a bit. But as I said, if you are looking at the qualitative results, the first thing is wellposedness. If you are working in a Banach space, which is not so desirable, in Banach space, we use the Hiller-Yoshida theorem, which again, everything turns around the linear operator A. So you reduce your complicated PD into an OD again. So you have U prime is equal to AU. So this A is the key thing for us. So again, the application of, for example, Hiller-Yoshida theorem is based on the properties of this operator A. We require this operator should be densely defined, closed operator, or we are looking at the resolvent of this operator. Of course, these are some deep knowledge we might not know at this point. I mean, you might not know. If you are working in a Hilbert space setting, then in order to prove the wellposedness of my PDE, I mostly appeal to Lömer-Phillips theorem. Again, these are all recipes. Just think about on a written book, you have the recipes to cook your meal, okay? So in this setting, you use this recipe. In this Hilbert space setting, you use this kind of recipe, but no matter which recipe you use, in everything, you have to use the properties of your linear operator A. And in actually Lömer-Phillips, for example, this is the second one is the one mostly we use in our models. In order to use this theorem, we have to prove that A is maximal dissipative, which means that A should satisfy this kind of estimate where these brackets represent the inner product. And also this operator should be surjective for some lambda 0. And generally in the proofs, the first part is relatively easier, not too easy, but compared to the second one, this is easier. The main problem is to prove this operator is surjective, because in order to do that, actually, essentially, we are applying the Laplace transform to our PDE system. We eliminate the t variable, and then we work with the static equations. If you have just static equations, it means that you don't have the evolution equation. For these kind of static equations, to prove the existence of the solution, our recipe is Lax-Milgram or Babushka-Bressi theorem. So mostly we use these two theorems. Of course, I'm not going to go into details. Again, so when we say qualitative analysis, again, as I said, we might look at the wellposedness, or we might look at the long-time behavior in the sense of stability, or asymptotic analysis, how the solution to your PDE will behave in infinite time. This is actually quite important in control theory, because in most of the applications, engineers or some biohealth people look at the things from this point of view. What I mean, for example, some biologists look at some cells, or whatever these cells are, maybe protein cells, maybe some cancer cells. So they would like to see how these cells move, and then how they behave after some certain time, large time, okay? Maybe, let's say in 6 months. This is also a time for us. So how these cells will behave. This is a kind of long-time behavior or asymptotic analysis for this for these cells. And the movement of the cells, of course, can be described via the partial differential equations. I will just talk about it in my future slides. So stability is kind of important in applied mathematics. This is what I mean. Okay, so if you are looking at this stability theory, the question is, what is going to happen with my PDE system after long period of time? For this, again, we can just separate the things, linear system or non-linear system. If you have a linear PDE, you're lucky, things are easier. But even in the linear case, you have to think about the things in two ways. Are you working in finite dimension, or are you working in infinite dimension? This is important because in finite dimension, again, as I said, you have a complicated PDE, you reduced it into this kind of ODE. In finite dimension, again, this is, I guess this is given in some of the ODE books. I don't know if you have ever seen it in your classes. If you have this kind of equation, and if you are in finite dimension, this A can be considered as a matrix. Just think about the 2 by 2 matrix or 3 by 3 matrix. In finite dimension, to consider the stability properties, you have to look at the eigenvalues of this matrix. Actually, it's taught in any OD book. With respect to the eigenvalues of your matrix A, you determine which eigenvalue is going to give you a stable manifold or unstable manifold, or stable subspace or unstable subspace. So, in short, in finite dimension, only the eigenvalues of A are going to determine the long-time behavior result or the stability of the equilibrium points. Why I say this? Again, if you reduce your PD into this kind of ODE, actually, when we say stability, you have to deal with the spectrum of this operator A. So in finite dimension, the spectrum of the operator A only consists of the eigenvalues. That's the reason we are looking at the eigenvalues of this linear operator A. But if you are in infinite dimension, unfortunately, the spectrum analysis is going to be more difficult, because in infinite dimension, the spectrum of this operator A is not going to consist of the eigenvalues only. So when we say spectrum, of course, this is kind of, again, deep subject. Probably you haven't seen it because generally it's given in PhD level. But when we say the spectrum of A, we need to analyze some different parts of spectrum, like the point spectrum, which refers to the eigenvalues of your operator A, but this is not enough in infinite dimension. So you have to refer to continuous and residual spectrums. So which means that in infinite dimension, things are more complicated, actually. But if you have a nonlinear system, then unfortunately you don't have this structure. Instead, your ODE can be given via a nonlinear operator or nonlinear function f. So what we can do, most people actually, even if they have a complicated nonlinear PDE system, they prefer to linearize it around some equilibrium points. When you linearize your system, then actually you have a linear system. Then you might use the technique given in this first case. So if f is nonlinear function, then you can use the linearization of f, which means that the linearization, the f is going to give you the Jacobian matrix. Then Jacobian matrix is going to behave like this linear operator A, and you can look at the eigenvalues of this Jacobian matrix to determine the stability points or stable or unstable points. But in infinite dimension, also in nonlinear case, of course, things are more complicated. So you have to appeal to some different techniques like the nonlinear operator theory and some maybe approximation results. Okay, so we say long-time behavior or stability results. It doesn't matter you are working in infinite dimension, linear or nonlinear model. If you have an autonomous dynamical system, and autonomous means you have, for this equation, for example, y prime is equal to ay, the right-hand side should depend on y only, just the dependent variable, then we call it an autonomous system. If you have this kind of system, then you might look at some stability results from different point of view. When we say stability, generally people ask what kind of stability we mean. There is a strong stability, which means that asymptotic decay, or once you prove the wellposedness, there exists a solution. Then if you are dealing with the strong stability, essentially you are trying to prove the solution, your solution to PDE system is going to zero when time is going to infinity. So at large time, your solution is just decaying to the 0 point. This is strong stability or asymptotic decay. Or you might see exponential stability, still your solution is going to 0, but with an exponential rate. So the inequality for the exponential stability is this that we need to obtain in our analysis. But if you prove the polynomial decay, then your solution is going to 0, but with a polynomial decay rate as given in this inequality. So which one is the best here? Of course, the exponential stability is the most desirable one, because if you have exponential stability, then automatically you have strong stability. Because exponential stability means your solution is going to 0 in a very, very fast rate. Okay, so after some introduction, or after some little bit knowledge how we look at the things in PDE analysis, so what are the applications? How we see partial differential equations and all these operator semigroups, or the analysis of these ODE systems, how do we see all these kind of stuff in the application? So the first application is given in biomedicine. So actually here you see a section of an human, let's say mammalian artery. Okay, so here in our tissues or arteries, the blood is flowing. Everybody knows this. This is a fact. So the blood is flowing here inside the artery. And these arteries have some vascular walls, of course, and these walls are separated with some elastic lamina. But all these walls have kind of layers. For example, here, this is the mammalian tissue, and the walls are called intima, media, and adventitia, and all these vascular walls are separated with some laminae here. But when the blood is flowing, of course, blood is considered to be the fluid, and this fluid is applying kind of pressure into your vascular walls, these parts, and with this pressure, the elastic walls are moving, and all this moving and the flow of your blood is kind of having an interaction, and this interaction gives rise to a complicated PDE. And why this is important? Because in biomedical applications, people are trying to explain the aneurysm, for example, with these kind of partial differential equations. Again, this is the normal artery, and the blood is flowing here. If you don't have any aneurysm issue, then as you see this normal picture, but if there is an aneurysm due to the existence of the pressure, then you see this bad picture here, and something is not good. Okay, and all this stuff is explained via the partial differential equations. And so from the biological picture, so how do we see the things in mathematics? Of course, this is the question. Again, for this kind of my first example is going to be multi-layered composite structure fluid interaction PDE system, and these systems firstly were analyzed with some researchers, Martina Bukac, Boris Muha, and Sani Kanik. They worked on these kind of systems, and they started with thinking this kind of mammalian arteries, and they say the interaction between the arterial walls and the blood transport and the blood happens in the blood transportation process, and how can we decrease, for example, the aneurysm? So this was the motivation point, and they started to work on these models in 2014. And again, they started with the theoretical point of view, and they proved for the complicated partial differential equation system, they proved the existence of solutions, weak solutions. I'm not gonna go into details. What's a weak solution? What's a strong solution? Of course, there is an explanation definition for it, but let's say they proved the existence of weak solution, and then they, using some different techniques, they look how regular these solutions are, and then they obtain some numerical results. They use some simulations, how this interaction gives rise to what kind of graphics, or how they affect this risk of aneurysm. So they just analyzed this stuff in 2-dimension, 1-dimension, 2-dimensional setting. Then motivated by this point, actually we started to work on our models, but also we realized that these kind of interaction problems occur also in cellular dynamics. For example, besides the blood transportation process, if you think about a eukaryotic cell, every cell in our body, in a human body, we have millions of cells, and these cells are always in motion, so they are moving. And each cell has a nuclei inside, and this nuclei is surrounded by an endoplasmic reticulum, and this nuclei has a membrane here. And actually here, from this biological picture, you see something static. It's not moving, but in the reality, these cells are moving. If you look at these pictures, this is the cell, this is the nuclei, and this is the membrane of the nuclei, this thin structure, but this membrane is moving when the cells move, and also this endoplasmic reticulum part is a fluid, and this fluid is also moving, and this fluid is applying kind of pressure or force to this membrane of the nuclei, and there is an interaction between this nuclei and this fluid, because this nuclei is giving a force from inside, and the fluid part, endoplasmic reticulum, is giving a force from the other side, and they have an interaction, on this membrane, and membrane is also moving. So all this stuff now can be conveyed to mathematics with this picture. So this is the cell. This is now motivated with the earlier works. We are working in a higher dimension. So this is three-dimensional fluid, which is the endoplasmic reticulum. This is the three-dimensional nuclei, and this is the membrane of the nuclei. So there is an interaction between the fluid and this structure, and this interaction gives rise to another partial differential equation, which models the motion of the membrane. You might ask here why we have a polyhedral domain instead of a smooth domain. This is just for the computational point of view. So we just wanted to look at the how the solutions can be approximated from the numerical point of view. So we just kept this as a polyhedral domain, but of course it can be a smooth domain, like in these pictures. It doesn't have to be corners. And as you see here from biology, when we pass to math, we see terrifying equations here. So this equation is the heat equation, or the fluid, the part of the fluid. So this is the endoplasmic reticulum. And this part, the middle equation, this is modeling the motion of the membrane of the nuclei, that thin structure. And this is modeling, this is a wave equation, it's modeling the motion of the nuclei. So the endoplasmic reticulum and the nuclei have an interaction over the interface, which is the membrane, which is modeled via this, again, another equation. Of course, from the physical point of view, there is an explanation why we give this equation with another wave. Actually, the left-hand side is coming from the energy and the inertia of this thin membrane, and the right-hand side is just the difference of the fluxes between the heat and wave equations. So there is a strategy to do this. This is not just randomly constructed. There is a rule to do that. And we see some boundary conditions here, and also we have the matching velocities, which is very standard in PD analysis. Of course, I'm not going to go into details. So from this complicated PDE, what we do, as I mentioned, so we can't find an explicit solution to this complicated PDE. It's not possible. So instead, since everything is linear, we can reduce this complicated PDE into an ODE. We can determine the generator of the system, and we can appeal to the operator semigroups to analyze the wellposedness and long-time behavior, as I mentioned in the first part. And for this kind of models, we started to work on them in actually 2019. Then we proved this model is well-posed, so we followed the recipe to prove existence, uniqueness of the solution. And then we proved that the solution also satisfies the strong stability. And if you remember, I gave some different definitions for the stabilities. Actually, we just improved this result, and later with my collaborators, George Avalos and Boris Muha, and also again with George Avalos, we proved rational decay rates. This is better than the strong stability. And recently, I worked with a slightly different model because this was a canonical model. So I worked with a more realistic model, which has the Stokes equation inside instead of the heat equation. I proved again the existence uniqueness of the solutions, and I proved there is an asymptotic decay to the zero state for these solutions. So this is what I mean. Very recently, I worked on this model. So this is the endoplasmic reticulum part. So instead of the heat equation is just a baby model. So this is more realistic. This is the Stokes equation. In fact, this has to be Navier-Stokes equation, but Navier-Stokes equation is a nonlinear equation, and the nonlinearity just complicating the things. So instead, we just keep it at this moment as linear by having the Stokes operator. So this is the endoplasmic reticulum, the fluid equation. Again, this is the membrane. This is the nuclei part. Again, the interaction occurs between these three dynamics. And I prove the wellposedness for this system. What I do, actually, let me here. For this complicated system, I reduce it to an ODE, as I mentioned in the first part. Here, my solution refers to this phi, but this phi actually has five different solution variables. U is the fluid part, HHT is the membrane, and WWT is the nuclei part. So I have five different solution variables, and I reduce my PDE into this kind of ODE system, where unfortunately, the linear operator A is given with as this complicated 5 by 5 matrix. So the only thing I need to do is to analyze the properties of this operator to prove that, for example, A is maximal dissipative for the wellposedness. And of course, I have to determine the domain of this generator by using some PDE techniques. So for the wellposedness, I prove A is an maximal dissipative. So for this, initially, I prove this kind of inequality can be proved, where these parentheses refers to inner product. This is the real part of this inner product. And after I prove this, I need to show this range condition holds or this operator is surjective. This is generally the hard part. And to prove this result, I have to use these static equations, and I have to solve these static equations by using the Babushka-Bressy formulation. Again, this is another functional analysis theorem. So I use too many functional analysis theorem in my work. And yeah, so after I proved these two stuff, I say I have a unique solution for this complicated PDE. Then the second question is, so how these solutions will behave? Can I prove an asymptotic decay? Are the solutions going to go to zero state after some certain time? Which means that actually, can you control your solutions after some certain time, or the solutions will just behave crazily? So this is the question. Since this is my solution, how this kind of solution will behave when time goes to infinity. Again, in my recent work, I proved that I can prove the asymptotic decay or strong stability. However, there is some complications there. For example, 0 is an eigenvalue for the generator, so I have to remove this corresponding eigenspace from my entire state space H. And I can only prove the strong stability in this left space, actually, because the 0 eigenspace is the null space of my generator A. So I can only work on the orthogonal complement. Of course, there are some reasons to do that, but it's a complicated theory. But still, I can prove my solutions will decay to the 0 state only in this left subspace. Fortunately, null space is just one-dimensional, so I just remove the one-dimensional subspace from the entire state space H. So I'm just working on the left part. So I can prove there is strong stability. To prove strong stability, my recipe is actually the Arendt and Beatty's result, which is given as for the generator of the system A, I'm looking at this spectrum. Here I'm looking at the eigenvalues. So this theorem just says that there shouldn't be any eigenvalue on the imaginary axis for the operator A. And then look at the all spectrum, and all spectrum intersection, the imaginary axis should be countable. Then your operator semigroup is strongly stable, or your solutions will decay to the 0 state asymptotically. So this is the recipe I use. Of course, again, I have to analyze 3 different spectrum parts, look at the eigenvalues, and use some functional analysis theorems for it. All right, so this was the first application. And second application is the compressible flow structure interaction PDE model, which arise in aeroelasticity. Mostly mechanical engineers are working on these kind of systems. So what do we mean by that? As you see in the picture, everybody knows, everybody sees the airplane wings. So when the airplane starts to fly, there is a very strong air coming to the wings of your airplane. And the wings sometimes flutter, right, due to this air. And actually, when we say the interaction between compressible flow and structure, flow part is the air. Air is a kind of flow. And the structure part is the airplane wing. And there is an interaction between the flow and the this wing, this structure. And this interaction gives rise to another complicated PDE system. And what is the main question here? Actually, engineers are trying to decrease the fluttering effects on this airplane wings, because it starts to flutter. It's dangerous, right, while the airplane is flying. So we don't want this. So how can we decrease the fluttering effect? So this is another question, which is tried to be explained via this kind of interactive dynamics. So here, when we say compressible flow, of course, we have to give explanation to we have to start with the Navier-Stokes equations. When we say maybe you already heard about Navier-Stokes equations. Mostly in fluid mechanics, people use this kind of equations. If you have a fluid in your environment, for sure, the motion of this fluid or the flow of the fluid is explained via the Navier-Stokes equations. They are very complicated equations. And when we say fluids, maybe the first thing we should look for what kind of fluid we are talking about, because fluids are, again, described in two ways: incompressible fluids and compressible fluids. When we say incompressible fluid, for example, water is an incompressible fluid, because during the flow of your fluid, the density of your fluid is considered to be constant. It's not changing with respect to the pressure of your fluid. So this kind of fluids, if the density is constant, it's incompressible. If there is a density, or if the density changes with respect to the pressure of your fluid, then this kind of fluid is considered to be compressible fluid. And the basic example is the air or gas. Gases are compressible fluids or flows. So when we look at these two equations, we see the first one is the continuity equation coming from the conservation of mass, and the second one is the Navier-Stokes equation. Again, since we talk about a compressible, because we are looking at the interaction of the air, which is a compressible flow, and the airplane wing, which is the structure, that's the reason we start with the compressible Navier-Stokes system. So the first one is the continuity equation coming from the conservation of mass. This is the Navier-Stokes equation. And this models the fluid part or the flow, compressible flow part, and density here given with the rho, and P is the pressure of your flow. And unfortunately, density is not a constant, which complicates the things, because for compressible equations, you have additional variable. This is the hard thing here. And V is the fluid of your velocity. Actually, in continuum mechanics, compressible or incompressible fluids are categorized with respect to Mach number, and the Mach number is explained as the ratio between the velocity and the local speed of the sound of your fluid. So if this is greater than 0.3, then these kind of fluids are considered to be compressible fluids. But again, as I gave examples, compressible is air, incompressible is water. Okay, so what we do, again, we don't want to work with a nonlinear system. So what we do instead, we take an equilibrium point, just like that, and we linearize our complicated PDE system around this equilibrium point. And here we consider our compressible flow as a barotropic flow, which means that the pressure is considered to be the function of the density. So each of them is dependent on each other linearly. So this is important. And after the linearization process, from the nonlinear Navier-Stokes equation, I obtain a linear equation. And the Navier-Stokes nonlinearity after the linearization process gives rise to these two terms here. They are called Gaussian approximation. And this is the pressure equation or density equation. And now this is the fluid or flow, compressible flow equation. But these two equations just represent the flow part or the air. But when you look at this complicated, again, PD system, you see the pressure and the flow equation. But here the second equation or the third equation represents the motion of the airplane wing, okay? So this is the structure part. That's the reason we say the interaction between the compressible flow, which is the air, and the structure, which is the airplane wing, for example. So here we see three different dynamics with some boundary conditions, and these boundary conditions refer to so-called impermeability boundary conditions, which means that the first one says there is no tangential stress, there's no stress in the tangential direction. And this one says, actually in our geometry, our domain has two different walls, and S is the hard wall. It's kind of hard wall. So there is no fluid or flow passing through this hard wall. And here, as you see, omega is the part of the boundary where you give another revolution. So this is the elastic part. This is kind of moving, deforming. And we see here another boundary condition, which is called the material derivative boundary condition, which is pretty standard in terms of the flow structure interaction models. And here this is modeling the flutter of the airplane wing. This is kind of a plate equation, kind of, again, hyperbolic equation. And these boundary conditions are the so-called clamped boundary conditions. So there is an interaction between these two dynamics. Again, the problems can be, is this PD model well posed? And if it's well posed, how the solutions will behave. So of course, before starting to any kind of analysis, you have to determine what is your phase space. So I have four different variables: the pressure, the flow velocity U, and this is the structure displacement W, and W sub T, the velocity of the displacement. So I have four different variables for my PDE, and this is the phase space. So I'm working in this state space or phase space with respect to this inner product. Of course, just as a standard thing, capital U here, which was kind of the equilibrium point for the flow part. I have to put some assumptions to get some necessary estimates here. And again, the strategy is, I have a very complicated PDE. I can't do anything with it. So I have to reduce my linearized PDE system into an ODE system just like that. And here A plus B is the generator of my PDE. If this is the generator, which is explained via these 4x4 matrices, then the question is, can I explain the solution via the operator semigroups? The answer is yes. So by using the similar techniques, after reducing the PDE into an ODE, we explain the solution via the operator semigroups ST, and then we use the standard recipe to prove well-posedness and long-time behavior for these results. But of course, in all these works, we looked at the well-posedness or stability properties from a different point of view, so under some different conditions and different settings. But as I mentioned in the first application, to prove the qualitative properties, well-posedness and long-time behavior, all the strategies will be same, but just the model is different. Yeah, so I guess I should thank you.